Hi everyone! In this video we're going to go over some synthesis strategies regarding electrophilic aromatic substitution reactions. So in the first half of the chapter we talked about how to add different functional groups to an aromatic ring like benzene, and we saw that there are multiple reactions we can perform to add different functional groups. Now a few of them do involve two steps. So for instance, if you want to add an amino group to the benzene ring, you first need to nitrate it with NO2 and then reduce NO2 to NH2. Or if you want to add some halogens to the benzylic carbon, you first need to add that benzylic carbon. If you want to form a carboxylic acid, you also first need to add that benzylic carbon there. And finally, if you want to add a long alkyl chain or a branched alkyl chain, you need to first add an acyl group, and then you can reduce it. So I do recommend making flashcards for these reactions, or you can download the blank reaction map under modules study guides. So it'll look just like this one, except I've removed some of the reagents so that you can write them in and practice writing those reagents. All right. Now, when we're adding a second functional group onto the ring, things get a little tricky. Because remember, some of the groups we talked about were activators or electron donating groups, and those will add groups ortho or para, or they'll direct groups to the ortho or para position. Other groups are deactivators or electron withdrawing groups, and they're going to be meta-directors. So some things that we might have to keep in mind is, for instance, let's say we start with our nitro group and we want to add something ortho or para to the ring. Well, we might have to first reduce NO2 to NH2 because NO2 is a meta-director while NH2 is an ortho-para director. Down below that, we have a ketone bonded to the benzene ring, or an acyl group, and that is a meta-director. But once we reduce that to an alkyl group, now we have an ortho-para director. So you might have to fit in a second step in between these reduction or oxidation steps, where you add your second group before the reduction or oxidation. And there's other examples given in this table as well. You can find it in the same chapter that we've been covering. So let's go over an example where we might have to kind of put a second step in there. Okay, so let's say we're starting with benzene, and we want to eventually form this product where we have an amino group meta to a chloro group. Okay, so the first thing we want to do is figure out if these two groups are ortho-para directors or meta directors, because that will help us kind of strategize what order we should add the groups in. So let's start with NH2. Is that an ortho-para director or a meta director? It's an ortho-para director. All right, and what about chlorine? Is that a ortho-para director or a meta director? Remember, chlorine is our exception to the rule because even though it's weakly deactivating, through inductive effects, it is an orthopara director because it can donate electrons into the ring. So that's one of our exceptions. Okay, so knowing this information, let's take this a step back. So we'll use retrosynthetic arrows. All right, so what if we had started by adding NH2 first? And then what if we had started by adding chlorine first? So looking at aniline, actually let me give myself a little more room here. So looking at aniline, where would chlorine add, knowing that NH2 is an orthopara director? So it would add ortho or para. And that does not give us the product that we want. Okay, so let's double check our other option. What if we add chlorine first? Where would our NH2 group add? Well, we also said chlorine's an orthopara director, so presumably that second group would add orthopara. But we want NH2 to end up meta. So that also doesn't work. So what are we missing here? Well, remember, in order to form NH2, we said earlier you have to start by nitrating the benzene ring and then reducing it to NH2. So let's write that in. So again, remember, we would have to start by nitrating the benzene ring and then reducing that into NH2. Okay, so now let's look at NO2. Is NO2 an orthopara director or a meta director? It's a meta director, right? And that's exactly where we want chlorine to end up, is in the meta position. So what we're probably going to need to do is squeeze a step in here. I'll just draw it kind of down below. Oh, whoops. I drew my arrow in the opposite direction. So we would add a step in here where NO2 would direct chlorine to the meta position, and then we would go up to aniline. We would reduce NO2 from there. So that means this pathway off to the right doesn't work, but the pathway to the left does work. So let's rewrite that pathway because it's a little messy right now. All right, so we said the first thing we would do is nitrate the benzene ring. And which reagents would we use to add a nitro group? Nitric acid and sulfuric acid. All right, and then we're going to add the chlorine because it will add meta, given that NO2 is a meta director. And how do we add a chloro group to a benzene ring or an aromatic ring? We use Cl2, but we need a catalyst. So which catalyst do we use? Aluminum trichloride. Okay, and now in the very last step, we can reduce NO2 to NH2 to give us our final product. And how do we reduce NO2? So there are actually two steps here. In the first step, we would use a catalyst like zinc or iron. I just like to use zinc. And then we would also use hydrochloric acid in that step. And then in step 2, we use sodium hydroxide. Okay, so that is our full synthesis. So again, sometimes in between your reduction step or your oxidation step, whatever it might be, you have to add another step in order to get your second functional group in the right place. So just something to keep in mind. Now, let's also talk about a couple of tips or rules that we need to follow when performing these synthesis reactions here. So tip number 1, let's say you have aniline and you want to add a nitro group onto the ring. So normally we would expect NO2 to probably add to the para position just because NH2 is a little bulky. However, this product is a really gooey product and it's really difficult to work with, so we often want to avoid this reaction. So unfortunately, this reaction is not a good one, so we try to avoid it. But again, that's if you have aniline and you're trying to add a nitro group. Okay, and then the second tip is if you do have a strongly deactivating group, like NO2 on your ring, and you want to perform Friedel-Crafts alkylation or acylation. So let's just write some reagents as an example. Unfortunately, this does not work because the ring is way too deactivated. So this reaction would be far too slow to occur, and the ring wouldn't even want to try to attack that acyl group. So Friedel-Crafts alkylation or acylation does not work if ring is too deactivated. So in general, we want to wait to add any electron withdrawing groups or deactivators until the last step. And then try to pay attention to the reaction order as well. Because sometimes you'll come across something like this where you'll realize, oh wait, I can't do Friedel-Crafts acylation here because of the NO2 group. So always just double check that you're going in a good order. So let's do a practice problem where we have a longer synthesis, and we'll try to kind of figure out the right synthesis or the right series of steps. Okay, so let's say again we're starting with benzene, and we want to end up with a nitro group on the upper left, an acyl group on the upper right, and then a bromine on the bottom left. All right, so let's figure out how best to synthesize this product. And by that I mean, what order are we going to add these groups in? Do we add nitro first? Do we add the acyl group first? Or do we add bromine first? And then what do we add second? So typically what I do for these types of problems is I work backwards. I use retrosynthetic analysis. And let's just start by figuring out, okay, if I go one step back, what are my possibilities? Okay, so let's say we have not added bromine yet in this second to last step. Okay, so we've added the nitro group and the acyl group, but we haven't added bromine. Another possibility is we added the acyl group and the bromine, but we haven't added the nitro group yet. And then our last possibility, we've added the nitro group and the bromine, but we have not added the acyl group quite yet. All right, so let's go through each of these different scenarios and see which ones make sense, which ones don't work, and that will help us narrow down the right pathway. So let's start with the reagent on the far left. So we've added the acyl group and the nitro group. All right, let's see where bromine might add with these two groups there. So let's start with the nitro group. Is that an ortho-para director or a meta director? A meta director, right? So let's see, one of the meta positions is already blocked by the acyl group, but we do have one meta position available. However, we want bromine to add here. So that doesn't really make sense, but let's double check the acyl group. Is the acyl group an ortho-para director or a meta director? So it is a deactivator or electron withdrawing group because remember we can move electrons up towards that oxygen. So that makes it a meta director. So it would also want to add bromine to the meta position. And again, we want bromine to add para to the acyl group. So this eliminates this as a possibility. So this doesn't work because bromine would not add to the desired location. All right, now let's go to our middle option. So it looks like we've already added bromine and the acyl group, and let's see where the nitro group might add. Okay, so we already said that the acyl group is a meta director. So where are the meta positions on the ring relative to the acyl group? On the upper left and on the bottom, right? Okay, and what about bromine? Where would bromine direct a second group? So remember, halogens are the exception. Even though they're weakly deactivated, they are ortho-para directors. So bromine would want to add the nitro group to the ortho position or the para position, but notice that the para position is blocked by the acyl group. So that's okay, but this works out because both bromine and the acyl group want to add nitro to the same place. And it doesn't matter which side the nitro group adds to, because you can flip it like a pancake and you'll get the same thing. All right, so that looks like a promising direction for our synthesis, but let's just double check the last option. All right, so we already said that the nitro group is a meta director. So let's see, we said one meta position was on the bottom. The other meta position would be right where the acyl group is desired to end up. We also said bromine is an ortho-para director. So ortho and para. Okay, so that looks like it also works. But remember, on the last slide, we said if you have a nitro group, that's going to highly deactivate the ring. And if you try to add an acyl group, you can't. There's no reaction because the ring is so deactivated by that nitro group. So that is going to eliminate this possibility because the ring is too deactivated. All right. So the central option is our best option because we're adding the electron withdrawing group last. The ring isn't too deactivated, so we can perform that reaction. And which reagents would we use to add the nitro group? Nitric acid and sulfuric acid. All right, so I'll just highlight this arrow since this is the correct pathway here. All right, so now that we figured out, okay, we're going to add the nitro group last, let's figure out whether we add bromine first or the acyl group first. So we're going to go backwards one more step. And we've got two possibilities. So in the first possibility, we add bromine first. In the second possibility, we add the acyl group first. So let's figure out which one is added first, or which one makes sense. All right, so we already said bromine is an ortho-para director. Okay, so it looks like that should add the acyl group right where we want it to. And bromine is quite large, so the acyl group probably wouldn't add to the ortho position necessarily. It would probably more so add to the para position. But let's double check our other option. So the acyl group we said is a meta director. So that would add something to these positions that I've drawn little stars next to. And we would want to add bromine to the para position. Okay, so that option just does not work. It wouldn't add bromine to the correct place. All right, so it looks like we have our pathway, and I'll highlight this arrow as well, because the step before this step was a benzene ring. Okay, so now let's just figure out which reagents we would use. Okay, so let's start with our first step, benzene to bromobenzene. How do we add a bromo group to the benzene ring? Br2, and what's our catalyst? Iron tribromide or aluminum tribromide, either one works. All right, in the next step, we want to add that acyl group. So which reagents would we use? So our acyl group would initially be bonded to a leaving group like chlorine, and then we'd use aluminum trichloride as our catalyst. Okay, so those are our 3 steps to get to the correct product. So it takes a little bit of trial and error to figure this out. So I often use a scratch piece of paper to work through these problems, and then I just neatly write the actual synthesis on whatever paper I'm using. But let's do one more problem just for some extra practice here. So let's say you're starting again with benzene and you want to end up with the following, where you have an amino group meta to a propyl group. How would you do this synthesis? And I encourage you to try this problem on your own first, and then when you're done, you can unpause the video and we'll go over it together. All right, so again, we want to always start by figuring out if the groups that are on our desired product are ortho-para-directors or meta-directors. Okay, so let's start with our propyl group. So that is an alkyl group. Is that an ortho-para-director or a meta-director? It's an ortho-para-director. All right, what about NH2? That's also an ortho-para-director. Okay, so we kind of run into the same scenario that we did before, where we want these two groups to end up meta to each other, but they're both ortho-para-directors. Okay, now one thing that I am going to keep in mind is how I actually create these functional groups. So looking at NH2, I know that to form that group, I actually have to start with a nitration. And then I reduce the nitro group to form NH2. Okay, and then the alkyl group, remember if you want to form that chain or some sort of long chain of carbons and hydrogens on your benzene ring or aromatic ring, you first have to start with an acyl group and then reduce it to the alkyl group. So what we actually want to analyze is NO2 and the acyl group. So let's look at NO2 first. Is that a meta-director or an ortho-para-director? It's a meta-director. So it does want to add an acyl group to the correct place, but what's the problem here? Remember, NO2 is highly deactivating, so we cannot perform Friedel-Crafts alkylation or acylation, so that would not work. Okay, so that is not our starting material for the rest of this synthesis here. But let's look at the acyl group. Is that acyl group a meta-director or an ortho-para-director? It's also a meta-director, so it does direct the second group to the place where we want it to go. And it's not too deactivating like nitro is, so that is possible. Okay, so what that tells me is that we're actually going to form this acyl group first, then we're going to add the nitro group, and then we can do our reduction steps. So why don't we reduce the acyl group first and then add the nitro group? Because remember, once we reduce that acyl group, now we have an ortho-para director. So the nitro group wouldn't add to the right spot. Okay, so let's just write all this out more neatly. All right, so I'm actually just going to leave that acyl group drawing there. So what reagents do we use to add that acyl group? So we just draw the same group but with a chlorine on one end. And then our catalyst would be aluminum trichloride. And then we said in the second step, that's when we're going to add our second group to the meta position, because the acyl group is a meta director. Okay, so remember we have to add NO2 first and then reduce it to NH2. But how do we add that NO2 group? Which reagents do we use? Nitric acid and sulfuric acid. Okay, now let's reduce, let's see, how could we reduce both of these groups at the same time? We could actually use the Clemmensen reduction to reduce both of these groups at the same time. So we could use zinc and mercury with hydrochloric acid. Now we do have to actually follow that up with sodium hydroxide, mostly because under these conditions, the amino group would be protonated. And so we want to just remove that extra proton from the amino group. So let me just kind of write a note here. So instead of NH2, we would end up with NH3 if we didn't add that base at the end. All right, and again, this is a Clemmensen reduction. Okay, so I think we're going to stop the video there. Your pods this week are very similar to some of these problems that we've gone over. But if you need any help with those, just let me know. In our next video, we're going to talk about a couple of other types of reactions involving these aromatic rings. So we'll talk about nucleophilic aromatic substitution and elimination addition. So I will see you then.